Welcome to ZK Vibes, your go-to for zero-knowledge tech, scaling solutions, and the future of blockchain. Today, we're jumping into a deep dive, exploring a concept called native rollups, a pretty groundbreaking approach that could fundamentally reshape Ethereum's Layer 2 architecture. We've sifted through a stack of sources you shared to figure out, what they are, how they work, and why some people are calling them the scaling endgame for Ethereum. Okay, let's really dig in and unpack this idea of native rollups. What's the fundamental problem they're trying to solve here?
Right. So the core idea behind native rollups, and this comes from folks like Justin Drake, is really to tackle the complexity and, frankly, the potential security issues in how a lot of current rollups work. Think about today's EVM equivalent rollups. They often involve thousands, literally thousands of lines of custom code just for verification. Things like fraud proofs and optimistic rollups, or the snark verifiers and ZK rollups.
And that custom code. Yeah, that feels like a massive attack surface, doesn't it? The sources really hammered that point home, especially the risk in those proving circuits for ZK. Like a tiny bug there could potentially make a totally invalid transaction look fine.
Exactly. It's a significant risk. And because of that complexity, that inherent risk, many rollups today, they kind of have to lean on centralized measures, especially when they first launch. You see things like centralized sequencers or maybe security councils acting as necessary backstops, which, let's be honest, kind of pushes against the whole decentralization goal.
Yeah.
Plus, they often struggle to keep their execution perfectly in sync with Ethereum's own EVM upgrades. That usually means manual governance, voting, coordinating hard forks. It's cumbersome. And then there's the cost of actually verifying these custom proofs on-chain. It can be expensive, which leads to less frequent settlement batching.
Okay, so native rollups are pitched as the way out of this tangle.
Precisely. That's the vision. They're building on ideas that have actually been floating around the Ethereum space for a while, maybe since 2017 or so. The absolute key piece, the core innovation proposed, is using a new precompile right on Ethereum's base layer, something called the execute precompile. The whole idea is, instead of the rollup building its own complicated custom verification logic, it basically outsources that critical job directly to Ethereum itself using this precompile.
Ah, okay. So the rollup isn't inventing its own complex crypto approver code that L1 has to somehow understand and check. It's more like saying, hey, Ethereum, here's a transaction trace. Can you run this through your engine and just confirm the end result matches what I say it should?
That's a really good way to put it, yeah. The sources use this analogy of programmable execution shards. They take that core job, executing transactions, changing the state, wrap it up in this execute precompile, and then the rollup adds its own specific logic around it for things like sequencing, maybe bridging, other features. But the really sensitive part, the trust critical part, verifying the state transition is correct, that gets handled by Ethereum's own L1 validators.
And those L1 validators, they do this check off chain, right? Using maybe different clients or specialized software.
Yes. Exactly that. They might re-execute the trace themselves, or they might verify cryptographic proofs, ZK proofs, that the rollup generates. They'd use various tools, maybe specialized clients, sometimes called ZKEL clients, or, ZK VM infrastructure, all designed to efficiently check that the execution was valid. And it's really crucial to get this. The main goal of execute isn't necessarily about making the computation itself cheaper on L1 in isolation. The cost savings are more about batching tons of rollup transactions into a single L1 call and maybe down the line potential subsidies. The primary driver is enabling truly trustless rollups by letting them inherit Ethereum's L1 security directly without needing their own complex bug-prone verification code.
Okay, let's zoom in on that execute precompile then. What does it actually look like under the hood based on the materials we have?
So technically, it's a proposed addition to the Ethereum protocol. Think of it as a way to expose Ethereum's own L1 execution environment, the EVM basically directly to applications or smart contracts. When a rollup wants to use it, it provides 4 key things. The pre-state root, that's the state before the transactions.
Right.
The desired post-state root, the state after. The trace, which is like the detailed script of operations. And finally, the gas used exactly how much computation it took.
So it's like feeding the EVM a script and saying, confirm for me if I start here, run this script, do I end up exactly here using exactly this much gas?
Precisely. That's the function. The precompile takes that trace, runs it, starting from the pre-state root, and then cryptographically checks that it produces the exact post-state root claimed while consuming the exact amount of gas used. The sources also mention some kind of metering system, maybe like EIP-1515, to manage the overall compute load from all the execute calls happening in one L1 block.
Now, this is where it got really interesting for me. If rollups are literally using Ethereum's own execution engine via Execute, doesn't that just automatically solve the whole EVM equivalence headache?
It absolutely does, yes. That's one of the most powerful implications here. Because the rollup is running inside the native Ethereum environment provided by Execute, it just automatically inherits all future EVM upgrades, instantly. There's no need for the rollup to have its own separate governance to update its execution rules or coordinate hard forks with L1. It ensures perfect native alignment. It basically takes all that complex state transition logic of the rollup and boils it down to one single call that L1 validators just need to check.
Wow. Okay, that level of alignment is a huge deal. Now, the sources talk about how this native approach applies to the two main types of rollups we know, optimistic and ZK. How do they look different in this new world?
Yeah, the main differences come down to how they handle data availability and how they achieve finality. So, optimistic native rollups could potentially still use cheaper data availability options, like maybe Celestia or similar layers, for their day-to-day operations. They'd only really need to post the expensive transaction trace data onto Ethereum's own data blobs if there's a dispute, a fraud challenge. And Execute actually helps here because during a dispute, the L1 validators only need to check the specific small part of the trace being challenged, not the whole thing. This could allow for really large batch sizes, theoretically.
But the classic optimistic drawback is still there, right? That challenge period. You still have that waiting time before transactions are truly final.
Yes, that fundamental trade-off doesn't go away. Users still face that challenge window, could be days. And the sources correctly point out this slow finality isn't free. It has real, though sometimes hidden, costs. It locks up capital. It makes bridging more expensive because liquidity providers demand a higher premium for that longer risk period. It generally just reduces capital efficiency across the board.
Okay, so how does ZK native rollups compare then?
ZK native rollups approach data differently. They have to put all their transaction data onto Ethereum's own DA layer right away. That's because the validators need immediate access to the full execution trace to either generate or verify the ZK proofs. They're also potentially constrained, at least initially, by proposed execute cumulative Vegas limit. That's basically a cap on how much total computation can be verified via execute in a single L1 block. So it might limit their batch sizes compared to the potential of optimistic ones, especially if optimistic disputes are rare.
So why go ZK native then if you've got potentially higher data costs up front and maybe smaller batches, at least to start? What's the big draw?
The massive draw is real-time settlement, or as the sources call it, one-slot delayed execution finality. This essentially means users might only wait around 12 seconds at a time for one Ethereum block or slot for their transaction to be considered final. And crucially, they get this without needing the super fast, almost instant ZK, proving that current ZK rollups often strive for to give a good user experience. This speed is a game changer.
A game changer like? How? What benefits does that unlock?
Well, capital-efficient bridging is a huge one. Think about protocols like a cross. They rely on fast finality to minimize risk for their liquidity providers. Faster finality means lower risk, which should translate to lower fees for users bridging assets. It also opens the door to much smoother cross-rollup composability, and potentially completely trustless bridging using ZK proofs between native rollups, getting rid of the need for third-party bridges that have their own trust assumptions.
So just looking at the pure cost aspect, is it obvious which one wins out, optimistic or ZK native?
Actually, the sources are pretty careful here. They say it's kind of ambiguous in the long term. Optimistic native rollups might look cheaper operationally day-to-day because they can use cheaper DA layers most of the time. But then you have those hidden capital costs from slow finality. ZK native rollups, on the other hand, might actually end up being more economical overall if the real power of Execute turns out to be enabling really efficient batch verification, using snark recursion, verifying proofs about proofs. If that batching significantly cuts costs compared to how verification works now, ZK could be cheaper overall. But if Execute mostly just enables easier re-execution, then optimistic rollups, by ditching complex fraud proofs for simple re-execution via Execute, could become really competitive on cost too. It's genuinely hard to say without seeing how the practical costs of Execute batching with ZK actually shake out.
Right, makes sense. Let's dive into some of the deeper technical bits needed for this. The sources talk quite a bit about state transition and this idea of stateless verification. Can you break that down for us?
Okay, so state transition is just the basic process. How the blockchain's entire state, all the account balances, contract data, everything changes from one block to the next because of the transactions that were executed. Pretty fundamental. Stateless verification is more of a future goal for Ethereum. The idea is that validators could confirm these state transitions are correct without actually needing to hold a full, constantly updated copy of the entire Ethereum state themselves.
How is that even possible? How do you verify something without seeing the whole picture?
Yeah, it sounds a bit magic, but they rely on something called state access proofs. These are cryptographic proofs that get bundled with the transactions. They essentially prove, hey, this transaction only needed to read or write these specific pieces of the state, and here's proof of what those pieces were.
And why is this stateless vision so critical for native rollups?
Because it totally changes the job for validators. Right now, maintaining the full state requires massive amounts of storage, which is super expensive on Ethereum. Stateless verification shifts the burden mostly to computation checking these proofs. And for native rollups, especially ZK ones, ZK proofs make that computation really efficient. Validators just check these compact math proofs instead of rerunning everything or needing huge databases.
So how does this roll out in practice? What's the implementation path look like?
Well, the sources describe it as phased. They'd likely launch first using what's called simple re-execution. In this phase, validators use the execute precompile to literally just rerun the rollups transactions. It's straightforward but computationally intensive, so it might limit throughput. The long-term vision, though, is snark verification. Here, validators would just check these compact ZK proofs, these snarks provided by the rollup. This is expected to dramatically boost throughput and cut down validator overhead. The idea is, as ZK tech gets better, faster, cheaper, this snark verification would eventually replace the simple re-execution.
I've also heard about ZK fault proofs, kind of like optimistic rollups, but using ZK proofs instead of those back and forth fraud games during a dispute. Where does that fit?
Yeah, the sources mentioned that. While ZK fault proofs are technically possible, they become less appealing as ZK proving gets cheaper. Why? Because they still have the fundamental drawback of optimistic rollups.
Right.
That slow finality from the challenge period. The capital lockup, the delays, those persist even if you swap out the dispute mechanism for a ZK proof.
And there was a point about bridging, right? Currently, L2s post state proofs onto L1, so L1 contracts can verify them trustlessly. But native rollup proofs are mainly off-chain. How does that work?
Yeah, that's flagged as one of the technical challenges still being figured out. How do native rollup bridges achieve that same level of trustless on-chain verification of the rollup state if the primary proofs live off-chain? It's an open question for bridge design.
Gotcha. And even with stateless verification, where validators don't store the whole rollup state long-term, they still need temporary access to some data, don't they?
They absolutely do. For the execute call to work, the validator needs temporary access to the full execution trace. Even though Ethereum's main data availability layer uses sampling DAS, data availability sampling, where validators only check small pieces of the big data blobs. The execute precompile itself needs the complete trace data to actually perform its verification check. So this does create some extra data availability overhead compared to traditional optimistic rollups, which really only need state proofs if there's a dispute.
Okay, so validators have this trace data, whether they're re-executing or checking snarks. How does that verification process actually function in this native model?
Right, so in the re-execution phase, it's straightforward. They take the trace, run the logic using execute, and see if the output matches the claimed post-state root and gas used. In the future snark enforcement phase, they'd still use the trace maybe to check it's well-formed, but the actual correctness of the state transition is guaranteed by the ZK proof generated by the rollup. These proofs get shared off-chain, maybe peer-to-peer, by whoever proposed the execution. The security link comes from consensus. Validators will only vote yes, attest to a new L1 block, if valid proofs for the previous block's execution are available and verified.
This brings us to something I found really fascinating, maybe even a bit counterintuitive, in the materials. There's no single standard ZK-proof format that Ethereum itself mandates, is there?
That's a crucial detail, yeah, and it seems quite intentional. The ZK proofs themselves, how they're generated, how they're verified, that mostly happens off-chain, outside the core Ethereum protocol spec. Ethereum might standardize things like the format for state access proofs, using Merkle proofs, but it's not dictating you must use the ZK proof system.
So different validators could literally be using different ZK proving systems.
Yeah.
Maybe one uses Succinct's tech, another uses Rutger Neo, another uses something else, all to verify the same block's execution trace.
Exactly. As long as the validator trusts their chosen system to correctly verify that the execute call parameters, pre-state, post-state, trace, gas, are consistent, the whole thing works. It means validators aren't checking each other's proofs. They're independently checking the validity of the execution trace using whatever client or ZK system they trust.
And the sources raise this really interesting point about that design. Is this complexity, this lack of a single proof standard, a necessary evil to avoid getting locked into one specific ZK technology too early? Or will we eventually see the ecosystem kind of converge on a unified standard anyway?
It's a major open question, absolutely. On the one hand, it allows for innovation and competition between different ZK teams right now, which is probably healthy for pushing the technology forward. But yeah, it definitely adds complexity compared to a scenario where everyone just uses one standard format. It really highlights how this tech is still evolving.
Okay, moving beyond state and verification. The sources also made it clear that pretty significant changes are needed in Ethereum's core consensus itself to make native rollups practical. Can you give us a quick refresher on how consensus works now?
Sure. So in the current proof-of-stake system, you have validators. Some are randomly chosen for each 12-second slot to be the proposer. They build the block, propose it, and earn rewards both from the core consensus, beacon chain rewards, and from transaction fees, or MEV, in the execution part. The other validators act as attesters. They vote on whether the proposed block is valid, and that's how the chain gets finalized. We also have proposer-builder separation, or PBS, often implemented via things like MEV boost, that tries to separate the proposing role from the block-building role to encourage decentralization, although sometimes sophisticated players vertically integrate and kind of centralize parts of it anyway.
Right, and this is where attested-proposer separation, or APS, comes in as a proposed future change.
Exactly. APS is like a deeper split. It separates the role of the beacon proposer, that's still a validator, doing core consensus, getting beacon rewards from a new role called the execution proposer. The execution proposer is specifically responsible for building the executable part of the block, the transactions, the state changes, and they claim the execution rewards like fees and MEV. And importantly, this execution proposer role is envisioned as being market-driven. Anyone who can profitably build and propose execution blocks could potentially compete for it.
Okay, how does APS link up with this other concept mentioned, delayed execution?
Right. APS is basically what enables one-slot delayed execution. Delayed execution is another key proposal aimed at tackling a bottleneck in how fast L1 can process blocks. Currently, the proposer has to do everything in that single 12-second slot, build the block, run all the transactions to figure out the new state, and get it attested. It's a lot. Delayed execution proposes splitting the block validation, just checking the structure, data availability, from the heavy lifting of transaction execution. Validators could quickly check the block structure looks okay and attest to its availability. Then the actual execution happens in the next slot. The sources suggest this could make L1 block processing maybe 5 to 8 times faster.
And that is what makes native rollups practical, especially the ZK ones.
Precisely. With APS creating the separate execution proposer role and delayed execution giving them time, it solves a major timing problem. The execution proposer for block N, which gets executed in slot N, now has the entire next slot, slot N plus 1, a full 12 seconds to generate those potentially complex snark proofs for block N's execution. Without that delay, the proposer would have to somehow generate those proofs in the same slot they're doing all the other consensus work, which just isn't feasible with today's ZK tech.
So let me get this straight.
Right.
Execution for block N happens in slot N. Proof for block N is generated in slot N plus 1.
That's the timing model, yeah. And the security holds because the attesters only vote yes on the execution component of block N plus 1 if the valid proof for block N's execution from the previous slot is actually available and checks out.
What if the execution proposer just fails? Doesn't produce the proof in slot N plus 1? I think the sources initially talked about altruistic provers stepping in, but then there was a shift.
Yeah, the initial idea did involve maybe altruistic provers jumping in to save the day, but that raised some obvious questions like, would there be enough reliable economic incentive for people to do that consistently, especially if generating the proof is expensive? So a more recent refinement mentioned is the same slot proof solution, which tackles this incentive problem more directly.
Same slot proof solution,
Mm-hmm.
even though the proof is generated in the next slot. The name is a bit confusing.
Yes, the naming can be a little tricky. The key isn't about when the proof is generated relative to the consensus slot, but about who has the responsibility and the incentive. With the same slot proof solution, the responsibility and the economic reward for generating the proof for block N is tied directly to the builder of block N itself. That builder must provide the valid proof in slot N plus 1 in order to actually claim their execution rewards from block N. So there's a very direct economic reason for them to make sure the proof gets generated.
Okay, that makes sense. And if they fail? if the builder just doesn't provide the proof?
There's a fallback mechanism. If the proof for block n is missing when slot n+1 comes around, the execution layer basically treats block n as a no-op. That means its state transition is just ignored. The state carries forward from block n1 directly to block n+1's execution. The chain itself doesn't halt, it maintains liveness. Light clients can still follow along. It just means the transactions in that specific block n didn't get finalized for execution rewards.
Wow. This whole timing thing seems to fundamentally change the game for ZK rollups, doesn't it? Like, instead of needing proofs generated in milliseconds to feel responsive, native rollups essentially get a whole 12-second slot.
Absolutely. That's a critical piece of the puzzle. It trades that one slot delay for the user in terms of when their transaction is truly final on L1 for dramatically more breathing room on the proving side for the network. It enables what the sources called real-time settlement without worrying about real-time proving. It potentially makes operating a ZK rollup much less dependent on having ultra-specialized, super low-latency proving hardware and infrastructure.
Okay, so pulling all these threads together, the execute precompile, stateless verification ideas, APS, delayed execution, same slot proofs. What does this all mean? Why are people calling native rollups a potential scaling endgame?
I think the core promise, the big picture, is that they fundamentally blur the lines between layer 1 and layer 2. By using Ethereum's own execution engine directly via execute, L2s stop feeling like separate systems with their own unique trust assumptions. They become more like true, secure extensions of Ethereum itself. This aims to create a much more unified, more secure ecosystem overall, minimizing systemic risk, because everything ultimately anchors back to L1 security in a very direct way.
And that unification, that should make interacting between different rollups much easier too, more trustless.
Exactly. That's a key part of the vision. With native rollups, one rollup could theoretically verify the state of another native rollup without needing extra trust assumptions or relying on complex, potentially risky third-party bridges. This opens up the possibility of truly seamless cross-rollup composability. Imagine users and protocols moving assets or calling contracts across different rollups much more easily and securely. The sources also touch on related developments like shared sequencers or based sequencers and shared settlement layers. These are all pieces trying to help rollups talk to each other more effectively in real time, although, fully automated, completely trustless cross-rollup interaction is still very much a work in progress.
So what's the realistic path here? When could we actually see this? What's the timeline?
Yeah, it's definitely not happening tomorrow. This requires some really fundamental changes to the Ethereum protocol itself. We're talking new EIPs, Ethereum improvement proposals for things like the execute, precompile, and delayed execution. The sources were pretty clear that deployment is likely not before 2026. It's a multi-year roadmap.
And it won't just suddenly appear fully baked.
No, definitely not. It's expected to be a phased rollout. It would likely start with that simpler re-execution method we talked about, probably under fairly strict gas limits for execute calls initially, so throughput might be somewhat limited at first, while the more advanced snark proving solutions, the ZK infrastructure, continues to get faster and cheaper.
Right. And speaking of challenges, the sources didn't really pull any punches. There's still some pretty significant technical hurdles to clear.
Absolutely. They highlighted several key ones, like the need for stateless verification means you have this witness data that adds significant overhead to data availability, maybe 5 to 10 times more data than traditional optimistic rollups need to post routinely. Standardizing things like deposit and withdrawal interfaces across different native rollups will be important for usability, and maybe most critically, the sources emphasize that only strictly EVM equivalent rollups could potentially transition to this model easily. Existing rollups that have diverged from the EVM would likely need substantial code refactoring to adopt this architecture. It's not just flipping a switch, it's a major architectural change for many.
Despite those hurdles, though, it seems like this vision has pretty strong support from key teams actually building the ZK technology.
Yes, the sources definitely pointed that out. They specifically mentioned enthusiasm from people building the underlying ZK tech. Uma Roy, the CEO of Succinct, was highlighted as being really positive about how native rollups simplify integrating ZK proofs deep into the protocol and how well it aligns with Ethereum's overall rollup-centric roadmap. Companies like Succinct, who provide that ZKVM infrastructure, are obviously going to be crucial players in making the proving layer work efficiently. And projects like ethproofs.org, which is like a public dashboard, tracking how well different ZKVMs perform in terms of cost and speed, are super important for driving the progress needed to make this whole vision practical.
So ultimately, the picture being painted is one where Ethereum really solidifies its role as the ultimate security layer, exporting its security guarantees to the layers built on top, but in a much more integrated native fashion.
Exactly, that's the endgame vision. For applications and assets that really need the highest level of security, Ethereum L1 is the gold standard. Native rollups offer a path to extend that same level of security, eventually, to compatible L2s. It's moving towards a future where rollups aren't just bolted onto Ethereum, but feel like truly trustless, integrated extensions of Ethereum itself.
That's a wrap for today's deep dive into native rollups and what they could mean for the future of Ethereum. We've seen how this proposed execute precompile, combined with fundamental consensus changes like APS and delayed execution, really has the potential to completely reshape L2 architecture. It offers a clearer path towards trustless scaling and maybe even seamless cross-rollup interaction, even while acknowledging, there are significant technical hurdles still ahead. If you're interested in diving deeper into ZK tech and Ethereum scaling, definitely check out resources from the teams and initiatives mentioned in the material, like Succinct and ethproofs.org.
And maybe here's a final thought for you to chew on, based on everything we've discussed. Given that adopting this native rollup model seems to require pretty extensive refactoring for existing rollups rather than just being a simple upgrade, how might that technical barrier, combined with the phased rollout plan and that strict need for EVM equivalence, influence which rollups actually thrive in the future? How might it shape the whole competitive landscape of the Ethereum L2 ecosystem in the coming years?
Great question. If you enjoyed this deep dive, be sure to follow us on ZK Vibes Twitter for updates, discussions, and more cutting-edge content on ZK Tech and Ethereum scaling. Thanks for tuning in, and as always, stay zero knowledge.